Hello, fifth grade. It's Wednesday, the 20th of May, 2020, and this is our science time. Disregard the stuff on the whiteboard. That's for our Zoom session. And so I just want to leave that up there. So that has nothing to do with science. But we are continuing with CompCheck 8.1. It was so long that I wanted to take the time to get the information carefully into you. And so we're going to read some more. We're reading about what causes weather. And we talked about that weather is caused by the sun. We talked about that. And that meteorologists are people who study the science of weather. We talked about different seasons. We talked about the way the sun hits the northern hemisphere at certain times directly and the southern at certain times directly. And that means our winters and our summers are opposite. And now we're going to talk about winds on page 205. And then we're going to look at our CompCheck, which is true and false. So it says the winds. Like the seasons, the Earth's winds are also created by the sun. Winds are produced by the temperature differences found on the Earth. The greatest of these temperature differences exist between the equator and the poles. Tropical regions near the equator are not greatly affected by the tilt of the Earth's axis. No matter what the season, energy from the sun always strikes there directly, making the temperatures constantly warm. But the north and south poles are just the opposite. Even in the summer, solar radiation reaches them in a slant and temperatures are cool. In the winter, they receive very little solar radiation and temperatures plunge to well below zero. At any given time, the temperature differences between the tropics and the poles are very great, as much as 180 degrees Fahrenheit. Okay, so I'm going to go through that with you again. We know that the winds are also caused by the sun. And it was talking about tropical regions that are near the equator are not greatly affected by the tilt of the Earth's axis. In other words, that temperature is going to stay relatively the same and it's hot. Okay, it's going to stay relatively the same. It's like it says, no matter what the season, the energy from the sun always strikes there directly, making the temperature constantly warm. Okay, but the north and the south pole are opposites. So they're as farthest away. The north is farthest away from the equator that it can be, and the south is farthest away from the equator as it can be. And so those have different temperatures, obviously, and they can have temperatures that are well below zero because they're farther from the equator. But the temperature around the equator is always hot because the sun is constantly directly shining there. Without winds, the equator would be much hotter and the poles would be much colder than they are now. God designed winds to carry excess heat away from the tropical regions and toward the poles. So the wind carries the wind to the northern pole and the southern pole, north pole and the south pole. And it keeps the equator from being too hot. According to the wise plan of the Creator, this transfer of heat not only balances out the uneven distribution of the sun's warmth on the Earth, but it also produces the clouds and systems of weather that water the Earth. But how exactly do the winds transport heat from the equator to the poles? Nothing but a lot of hot air. You have already learned that gases in the air expand when they are heated and contract when they are cooled. If air is heated, the molecules in the air spread out over a greater area, meaning that any particular area of space would hold fewer air molecules than it did before the air was heated. Cold air is denser, that means like thicker than warm air, and holds a greater number of molecules in the same amount of space. Since warm air is made up of more empty space and fewer molecules of matter, it weighs less than cool air. Cool air is heavy and has a tendency to fall and settle near the ground. Warm air rises when heavier, cooler air gets underneath it and pushes it upward. A good example of the rising power of warm air is seen in a hot air balloon. So look at the picture as I read this, okay? Air inside the balloon is heated and expands greatly. It is so much lighter than the unheated air around it that it is able to raise not just itself, but the balloon and the gondola, the place where the people ride as well. Okay, so There's a couple things I want to point out there. First of all, we know that heated air expands and cooler air contracts. And so if air is heated, the air spreads out. Cooler air is denser, it's thicker, it sticks together, but hotter air spreads out. And that's how it regulates itself. And it says cold air is denser than warm air and holds a greater number of molecules in the same amount of space, like I said. Since warm air is made up of more empty space and fewer molecules, it weighs less, and therefore that's what causes it to be able to rise. Imagine the difference. You're picking up something really heavy. It's harder to pick up than something that's much lighter, okay? And so that's why warm air rises. There's less molecules in a tighter space. There's less, and so it can rise. And so it can also carry, like the hot air balloon, it rises so much that it can carry the balloon and the gondola. All right, so we see in this picture, we're going to read that warm air is going to rise and cool air is going to come down, and so it balances, constantly balances. So easing the pressure. You will remember, I'm on page 206. You will remember that air pressure is the weight of the atmosphere pushing down on the earth. When warm air rises, it counteracts the downward push of the air's weight by moving in the opposite direction. Air that is moving up does not press down on the Earth's surface as hard as stationary air does. Rising air then actually reduces air pressure at ground level. In the same manner that an umbrella shields you from the rain or sun, rising air shields the area below it from the full weight of the atmosphere. Okay? I'm going to read that again. Rising air actually reduces air pressure at ground level in the same manner that an umbrella shields you from the rain or the sun. It pushes it away from you. Rising warm air shields the area below it from the full weight of the atmosphere. When cool air settles near the ground, it has the opposite effect on air pressure. Air pressure at ground level is increased, not decreased. The downward motion of falling air strengthens the normal downward push of the atmosphere's weight and adds to the total force pressing against the earth. Okay, so I want to read that again, and then I'm going to explain that. When the cool air settles near the ground, because we know that cool air, tighter, more dense, heavier, gravity is going to pull it down, so to speak. It has the opposite effect on air pressure. Air pressure at ground level is increased, not decreased. Okay, so the warm air decreases air pressure. I want to make sure that I have that right. Give me 1 second. So when the air pressure comes down, the warmer air kind of pushes, resists it, like an umbrella would shield us from the rain. It resists the rain. It holds the rain off of us. And so you can see the picture here that the warmer air is holding that colder air, okay? The colder air comes down, the air pressure is stronger, it's saying, and the downward motion of that falling air strengthens the normal downward push of the atmosphere's weight and adds to the total force pressing against the earth. When placed under high pressure, air seeks to flow to an area of lower pressure. Okay, it's just its natural instinct. For example, air under high pressure in a balloon will rush out of the balloon unless the end is tied. Okay, so you know you blow up a balloon and then you let it go and it spins all around unless you tie it. Okay, so in the atmosphere, air in a region of high pressure behaves like air escaping from a balloon. Air always flows away from a region of high pressure to fill in a region of low pressure. It always looks for a place to go, all right? And so here you have your picture. The warm air acts like an umbrella in our atmosphere. That's why we don't get too cold. And it keeps the air pressure normalized for us. And here you see the colder air is it's gonna, because of the density and the pressure and the weight and whatnot, it's going to the colder it is. It says that the downward motion of falling air strengthens the normal downward push of the atmosphere's weight and adds to the total force pressing against the Earth. That's what happens when cool air settles towards the ground. Okay? Page 207 shows you how to build a barometer, so we're going to go to page 208. It says Earth-sized winds. So be looking at the picture as I read this. In the tropics, the bright sun makes the Earth's land and ocean surfaces unusually warm. The Earth, in turn, heats the air above it. When warm air over the tropics rises because it is pushed up by cooler, heavier air surrounding it to the north and the south. The rising warm air creates low pressure below it at ground level. Cool air from both the north and south flows across the ground toward the equator to fill in the low pressure area. We talked about like the balloon. It's going to fill in that area. On the Earth, this flowing air is felt as wind. Okay? So look at the picture. You have your falling cool air. It meets with your rising warm air, and it has that cyclical event. That's air blowing. Okay? Air blowing. The cool air falls, because we talked about that before, in the page before, about the air pressure, and it's denser and stronger, or thicker, I should say, and the warm air rises, and so it circles. So the cool air and the warm air mix together, so to speak. At the same time that air near the ground flows towards the equator, air at the upper levels moves in the opposite direction. As the heated tropical air rises away from the warm Earth, it cools with the increase in altitude, height, until it is not light enough to move upward any further. Then it begins to flow away from the equator. As it moves from the equator, it cools even more and flows slowly downward to the Earth to replace the air moving at ground level toward the equator. The circulation is continual, like I said, with warm air rising at the equator, cooling and flowing outward, settling to the ground far to the north or south, and flowing back to the equator to be warmed all over again. Okay? And that is, let me double check some here. Yeah, so here's the picture. Here's our equator right here. Like I said, the blue represents the cold air, falls to the ground, warm air meets it, circulates it. So that's moving that warm air that we talked about a few pages before. That's moving that warm air out to warm the rest of the Earth, because remember, the equator is always warm, constantly warm. It takes that really warm air, this cooler air comes down, grabs that warm air, we know the heat rises, and it circulates. It circulates it. So it's moving that warm air away from the equator, and the farther it gets away, it gets into that thicker, denser, cool air, so it cools it, and it just constantly, continuously regulates it, or it would be way too hot near the equator. Okay, so air from the equator, our temperature from the equator is moved out by the winds. Okay, so that hot air is moved out, and the farther it gets away from the equator, the cooler it gets. So it cools itself, it regulates itself, and then it comes back down, heats up, cools itself, regulates itself, comes back down to the equator, heats up, cools itself. So it's constantly moving. A spin that makes the atmosphere dizzy. The Earth is a big place. It is so big in comparison to us that we never notice its motion. In the 365 days that make up 1 year, the Earth travels about 584 million miles, moving at 66,600 miles per hour. That means that if you are 10 years old, you have journeyed almost 6 billion miles in your lifetime. Pretty cool. But you didn't feel a thing. You probably had no idea that you were that kind of a cosmic traveler. And at the same time, as it is speeding through space in its track around the sun, the Earth also turns on its axis, completing one rotation in 24 hours. Okay? Of course, you know that the Earth's rotation causes sunrise and sunset every day, day and night, but you may not have known that in order for the Earth to keep up with its schedule of 24-hour days, the Earth's surface has to spin around at over 1,000 miles per hour. To us, the Earth appears to rotate very slowly, and the sun and moon seem to creep across the sky. But again, look what it says. The Earth's rotation causes sunrise and sunset. It rotates. A revolution of the Earth is 365 days. Okay. The rotation. I want to make sure I have the right terms here. Hang on one second. Yeah, the Earth's rotation is 24 hours. Okay, and the rotation is night and day. We have a daytime and a nighttime every 24 hours. Then we talked about the Earth's surface has to spin around at over 1,000 miles per hour. Do we feel that? To make our 24-hour day cycle? We don't feel that. To us, the Earth appears to rotate very slowly, and the sun and moon seem to creep across the sky, but it's literally going at 1,000 miles per hour. Okay? Only God. Only God. If the Earth did not rotate, the Earth's winds would be very predictable. Warm air would rise at the equator and flow all the way to the north and south poles, like we talked about, where it would cool and settle. Then, attracted by low pressure, it would flow along the ground back to the equator, warm up, and rise to begin the cycle again. To people on the Earth's surface, the winds would always appear to come from the north in the northern hemisphere and from the south in the southern hemisphere. So again, I just want to reiterate the whole thing we've been talking about when we've talked about the winds today is we're talking about how it comes at the equator, okay, and the warmer air and the cooler air. Okay, the warmer air comes from the equator, hits the cooler air, it cools it down, then it goes back, and it's filling in that low pressure. Low means towards the ground. It's filling in those spaces on the ground, like when you blow up a balloon and the air is going to go and expand the balloon. It's filling in the spaces. Okay, so that air, that low pressure is where that air goes that's filling in the air that's circulated. Okay, it's always seeking a place to go. All right, so the three major wind systems. So here you can see, like I said, circulation of winds if Earth did not rotate. Okay, it rotates for a purpose, and we talked about that. The three major wind systems. So look at the large globe on the bottom and look at all the arrows. The blues are for the cold weather, the oranges are for the warmer weather. It says the three major wind systems. The Earth's rotation makes the transfer of heat from the equator to the poles much more complicated. Rising air at the equator is not able to flow due north or south to the poles. It can travel only about a third of the distance before it falls back towards the Earth and gets caught in the return flow to the equator. The flow of air is not due north or south either. The Earth's rotation bends the winds so that in the northern hemisphere they blow from the northeast and in the southern hemisphere from the southeast. These winds in this part of the world are called the trade winds. So you could see the northeast trade winds, okay, blowing in one way, coming from one way. And then we have the southeast trade winds. All right, so these winds in this part of the world are called the trade winds. All right, I want to read that section again slowly while you're looking at the picture again so you really understand it. The Earth's rotation makes a transfer of heat from the equator. Remember, we get our heat from the equator to the poles much more complicated. Rising air at the equator is not able to flow due north, meaning north or south to the poles. It can travel only about a third of the distance before it falls back towards the Earth again and gets caught in the return flow to the equator. Okay, so it can't go from the equator all the way to the North Pole or from the equator all the way to the South Pole. All right, it can only go so far before it loses steam, so to speak. And so something has to come and pick it up to move it out more, so to speak. So it says the flow of air is not due north or south either. The Earth's rotation bends the winds so that in the northern hemisphere they blow from the northeast and in the southern hemisphere from the southeast. These winds in this part of the world are called the trade winds. Okay, so if it can only travel these winds about a third of the distance before it falls back towards the Earth, and then it comes back to fill in that empty space towards the Earth, The flow of air is not due north or south either. It can't get up as high north as it or as low south as it needs to. So it says the winds that flow so I want to back up. The Earth's rotation bends the winds so that in the northern hemisphere they flow from the northeast, and in the southern hemisphere from the southeast. These winds in this part of the world are called the trade winds. Okay? These winds are called the trade winds. The air flow, so you can look at the trade winds and the directions that they are blowing. So here's the equator. So they move the winds out from the equator, okay, out, and then they get picked up, taken to the poles. Okay, they move them out to the equator, picked up. The southeast moves them, they come down. The northeast, they go up. Remember, north up, south down. All right, so the airflow away from the poles is similar to the flow from the equator. Cold ground level air at the poles travels only about a third of the distance to the equator before rising and returning to the poles. Bent by the Earth's rotation, the winds in this part of the world blow from the east and are called the polar easterlies, okay? So this is cold ground level, not the warm air from the equator, but cold ground level air in the poles travels only about a third of the distance to the equator before rising and returning to the poles. So we can see the polar easterlies up here, okay? And we see the polar easterlies down here also. These are the poles, North Pole, South Pole. They can only go as far, so they need, before they fall back down to Earth, to be heated by the equator, they need to get there, so they're going to be caught up by the polar, well, we're not quite there yet. So I'm going to read that part again. Cold ground level air at the poles, travels only about a third of the distance to the equator before rising and returning to the poles. Okay? Bent by the Earth's rotation, the winds in this part of the world blow from the east and are called the polar easterlies. So look at the polar easterlies. In between the trade winds and the polar easterlies lies a region where the tropical and polar air flows meet. Okay? So before, the polar easterlies, cold air, North Pole, cold air, South Pole, the trade winds on the equator, okay? East. So we have the northeast trade winds and the southeast trade winds. And then we talked about the polar easterlies on the poles. Now the polar westerlies are going to fill in those blanks. Okay? So we have the hot air at the equator. We have the cold air, North Pole, South Pole. The winds can only rotate so far in the polar easterlies, north and south. Okay? And the winds and the trade winds can only go out so far from the equator. Some going south, some going the northeast and the southeast trade winds. There's got to be something in the middle that helps pick them up from the equator, carry them to the poles, from the poles back down to the equator. And those are going to be, they actually are collisions. So listen carefully. It says, in between the trade winds and the polar easterlies lies a region where the tropical and polar air flows meet. In these middle latitudes, the winds, affected both by the Earth's rotation and by the pressure differences between the airflows, blow out of the west. The areas in both hemispheres are referred to as the regions of prevailing westerlies. Okay, so again, in the middle of these latitudes, the winds, affected both by the Earth's rotation and by the pressure differences between the airflows, blow out of the west. And those are called the prevailing westerlies. So you could see the easterlies are going, this is east, are going towards the east in both of these pictures, going towards the east, but then the westerlies are going out towards the west, whether they're blowing from the southern hemisphere or the northern hemisphere, okay? And it says collisions between warm tropical air and cold polar air, the easterlies and the westerlies, give the middle latitudes the most changeable weather on Earth. Okay, so I'm going to do my best to explain that. Look at your picture. So you have your polar easterlies. These are very cold areas. They stay cold. They don't warm up much at all. South Pole, cold. North Pole, cold. Equator, really, really hot. We have our trade winds that blow, but they can only blow so far, okay? We have our polar easterlies, cold, 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 blow, keep it really cold there. Cold, 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 blow, keep it really cold there. Trade winds, hot, 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 keep it really hot there. We need our prevailing westerlies to come in the middle and to join this hot region with the cool region, okay? To keep things balanced there. And that's why here and down here, remember it's cold down here as well, that's why here in the middle is where you would have your the earth, the weather patterns that change the most. That's where you're going to get snow. That's where you're going to get a lot of rain. That's where it's going to be hot too in the summer. So the weather changes mostly in those regions. It's unstable because it's moving around the hot air. It's colliding with the hot and the cold. And so there's more weather changes in those areas. So you can see where the United States falls and in the middle of our country, that's where we can get the most weather changes. Okay. So it's pretty complicated, but look at the pictures. Don't stress about it. You just have a general idea that the sun controls our weather, that our winds help moderate the climate. It's really hot at the equator, and our winds come and carry the hot and the cold, come down from the trade winds and the easterlies, and they meet in the middle and the westerlies, and the westerlies kind of spins them around to create some kind of comfort level, some kind of, so we're not too hot or too cold. Okay, so for your comp check, I believe you have a template for this. If not, we'll talk about it in Zoom tomorrow, and if not, I'll show you how I want you to do it. But you know how to do true and false. If it's true, you write true, and you write the sentence as true. If it's false, you write false, and you make the statement true. For example, number 1 says, the Earth's rotation is the basic cause of all weather. Okay, we learned in day 1 that the sun is the constant cause of all weather. So you would write false. And then in the sentence, you'd write the sun is the basic cause of all weather. Okay, so you write false and you make the statement true. Okay, so you know how to do that. And we will check on Zoom and I'll see if you have any questions.